Hello students, welcome back to lecture 6 in the lecture series of multirate signal processing. Today we are going to discuss analysis of some simple multirate structures, and thereafter we will also see the multi-stage implementation of sampling rate conversion. In the previous lectures, we have studied about some typical identities which help us in realizing the complex multirate structures computationally efficient. So now, in today's lecture, we'll start with a analysis of a simple multirate structure. Let us consider a multirate system shown in the figure, and now our job is to determine y of n as a function of x of n. The solution of this particular problem leaves us with a important point of discussion, and I'll summarize at the end of this solution. Let us proceed further for solving this and trying to know about this y of n. I make use some intermediate points here so that the analysis becomes slightly easier, and also it becomes quite clear to understand. I have divided these points as v of n and identified this particular point after upsampling as vu of n, and this block is to create a delay, and after this particular block the output will be equal to vu of n minus 1. Similarly, here the delay is performed at the input end itself, and therefore a input is delayed by 1 unit. We are writing it as x of n minus 1, and then performed the downsampling operation, and the output is identified as w of n. Once w of n is given as an input to the upsampler, and we consider the output as w of n. So whenever we note here, the corresponding output y of n is equal to the summation of vu of n minus 1 and w of n. That is what we are trying to find. Therefore, so my approach for solving this problem is something like this. Let us identify some x of n which has its amplitude values ranging from n is equal to 0 to somewhere 8, 0, 1, 2, 3, so on until 8. I consider the magnitudes of that x of n at this particular time instance is equal to x of 0, x of 1, x of 2, so on until x of 8. This serves as the input for us. Now I supplement this particular system with this input x of n, and I am trying to calculate v of n. V of n is the output after downsampling it with a downsampling factor of 2. As we know that downsampler removes the samples m minus 1 samples in between each of the samples of the input sequence. Therefore, the resultant sequence will be equal to x of 0, x of 2, x of 4, x of 6, x of 8, and so on. Since we know that it removes m minus 1 samples, here m minus 1 is equal to 1, therefore we lose one intermediate sample between each of the samples of the sequence. Therefore, we have lost x of 1, x of 3, x of 5, x of 7, and so on. And the resultant sequence is something like this: x of 0, x of 2, x of 4, and so on. And now this particular sequence is given as an input to the upsampler with an upsampling factor of 2. Therefore, the corresponding output vu of n will be having L minus 1 zeros in between each of the samples of the input sequence. Therefore, the corresponding output is now written as x of 0 substituted with a 0 in between these two samples, therefore 0, x of 2, 0, x of 4, 0, x of 6, and so on. And this is what our VU of n is, and this completes the first part. However, we need to perform a simple delay here, but I will be doing it at the end so that we can add VU of n minus 1 and W of n directly to get Y of n. Now, coming to the second part, I will proceed from here, where x of n is now delayed by x of n minus 1. Therefore, I identify x of n minus 1 as a delay created on this input sequence, which is now written as x of minus 1, x of 0, x of 1, x of 2, x of 3, so on, typically delayed by 1 unit, and that's the reason we observe at time n is equal to 0 we have the amplitude of x of minus 1 sample, and similarly at 1 we identify the delayed version of x of 0, so on. This is what our x of n minus 1 is, and now this x of n minus 1 serves as an input to the next block, which is a downsampled by a factor of 2. Let us consider the output W of n in this case, and in such case W of n is equal to, since we lost m minus 1 samples in between, therefore the output of downsampler is now given as x of minus 1, x of 1, x of 3, x of 5, x of 7, x of 9, so on. This is how we got our W of n. This is a result of the downsampled sequence, the downsampled version of the input sequence, and now this W of n is given as an input to an upsampler with an upsampling factor of 2. Therefore, the output is identified as W of n in this case, and therefore W of n is given as x of minus 1. Since it introduces L minus 1 zeros in between, therefore the output sequence is equal to x of minus 1, 0, x of 1, 0, x of 3, 0, x of 5, 0, x of 7. All these outputs are written with respect to the time instance from 0 to 8 for our convenience. However, here there was a little discrepancy with respect to this rows and columns. I consider my request for the audience to just go through this perfectly. And now VU of n minus 1, VU of n minus 1. So since we are only left with the addition of these two outputs now in the first and second cases, now I would like to calculate the VU of n minus 1 and represent it here as VU of n minus 1 is a delayed version of VU of n, and therefore it will be 0, x of 0, 0, x of 2, 0, x of 4, and so on. And Y of n is equal to the addition of W of n and VU of n minus 1, where I have written here Y of n is equal to VU of n minus 1 plus W of n, WU of n. Therefore, so by addition we will be getting directly this as x of minus 1, x of 0, x of 1, x of 2. Since x of 0 plus 0 yields us x of 0, x of 1 plus 0 yields us x of 1, 0 plus x of 2 yields us x of 2, so on. Surprisingly, the fact that we got the output as the delayed version of the input signal, that is, we have started with x of n, where we have represented the magnitude as x of 0 to x of 8, but surprisingly the output was equal to a unit delay created on x of n, which is equal to x of minus 1, x of 0, x of 1, x of 2, and so on. A multi-rate structure in which the output sequence is delayed and scaled replica of the input sequence is generally called as a perfect reconstruction multirate system, and the structure shown above on this particular problem is a very simple example of such system. Since we have already calculated the proof for this particular perfect reconstruction property in time domain, I request I leave this formal proof of this perfect reconstruction property of the multirate structure shown in this problem as an exercise for the students. Just go through this problem and try to solve it using frequency domain and check whether y of n is equal to a delayed version of x of n or not. And this can be considered as a formal proof for your perfect reconstruction property of the multirate structures. Now, let us move forward. For considering the multistage implementations of sampling rate conversions. Generally, in sampling rate conversion, when the sampling rate conversion factor I, or generally we have used L in our discussions, when the sampling rate conversion factor L or M is very large, then the multistage sampling rate conversion will be a computationally efficient realization. So let us start with our multistage structures for interpolation. In interpolation, if sampling rate multiplication factor I is very large or L is very large, in such a case, then L can be expressed as a product of positive integers like L1, L2, L3, so on until Ln. In such cases, the interpolation by sampling rate multiplication factors L1, L2, so on until Ln are implemented separately, and then overall interpolation is obtained by cascading the n stages of interpolation as shown in the figure. In cascading of these interpolators, the anti-aliasing filters are introduced at the output of each stage of interpolation in order to eliminate the images introduced due to this upsampling in that stage. Similarly, in decimations too, if the sampling rate factor D or M is very large, then M can be expressed as a product of positive integers such that M is equal to M1 into M2 into so on until Mn. So now the decimation by sampling rate reduction factors M1, M2, so on until Mn are implemented separately stage wise, and then the overall decimation is obtained by cascading the n stages of decimation as shown in this figure. In cascading of decimeters, the anti-aliasing filters are introduced at the input of each stage to limit the bandwidth of the input signal to decimeter in order to avoid aliasing due to decimation in the spectrum of the output signal of that stage. This can also be identified as some simple identities, where if we have something like if x of n is an input, then you can consider m1, m2 as two different decimation factors given to y of n, then the equivalent structure can be simply replaced with one block which is equal to m, where m can be identified as a sampling reduction factor which is equal to the product of m1 and m2. I'll be using this multi-stage implementation of sampling rate conversion in the analysis of a simple example shown on the next slide. Let us consider a simple example in order to use the identities that what we have discussed until now, and also we will also apply the multi-stage implementation of the sampling rate converters that what we have discussed just now. Let us consider a simple problem where we need to determine the y of n in terms of x of n for the given multi-rate structure. Here we have a cascade of a upsampler with a factor of 4 and then a downsampler with a factor of 12 and once again an upsampler with a factor of 3. The solution for this particular problem is followed. Let us consider the block diagram shown in this particular figure, and now using multi-stage implementation that what we have studied, I would like to split this particular block with a downsampler which has a downsampling factor of 12, such that which can be written as a product of two factors like 4 and 3. This 12 can be written as a product of two factors 4 and 3, and this block is now split into two downsamplers such that it can be identified as a downsampler 4 and followed by a downsampler 3. When identified, the above problem block diagram will be in this fashion, where we will be having a upsampler with a upsampling factor of 4 and a downsampler with a downsampling factor of 4 and so on. So let us use the identity 2 that what we have studied in the previous lecture, where whenever an upsampler followed by a downsampler with a upsampling and downsampling factor equal, in such a case you can identify the output of this particular system will be simply equal to x of n itself. We have realized this with an amplification factor of 1 yesterday, and therefore I use that particular identity 2 in order to replace this particular block diagrams with a amplification factor of 1, so that at this point the output will be still equal to x of n. After reduction, so now our particular block diagram looks in this fashion, where x of n is given to a downsampler of a factor 3 and then an upsampling factor of 3. So once again, by using the identity 3 that what we have discussed yesterday, so now we can guess this output y of n. This y of n is a simple multiplication of x of n and then a Coombe sequence c of n, where c of n is equal to 1 for all multiples of this L or M, which is equal to 3 in this case. Therefore, when multiplied with such a Coombe sequence, now our output y of n will be simply equal to x of n, when only for the values of n is equal to the multiples of L and M here, which is equal to 3. In such case, this is equal to 0, 3, 6, 9 and so on, and it is 0 otherwise. Therefore, the corresponding output y of n will be simply equal to x of 0, 0, 0, x of 3, 0, 0, so on. we have already, as asked in the problem, we have already determined the output y of n in terms of input x of n, and we have represented it as y of n is equal to x of n into c of n. It is important to identify this c of n as a unit sampled sequence only at multiples of L or M, which is equal to 3 in this case. That's it for this lecture. If you have any kind of issues or doubts, you can raise a comment in the comment section. Thank you.